आवाज नहीं आ रही सर।
I have not yet started, sir. So just waiting for the students.
ओके
Just
सर।
let me know once you want me to start.
Sir, you can start.
Okay, fine. Okay, so let us get back to our discussion with the Opti system and Optifiber. So yesterday, those who were present, they can understand that we had a discussion regarding introduction to optical fiber communication. Along with that, with a precise focus on Optifiber, which is basically used for optical fiber communication designing. So, just a second. So basically, we had a discussion regarding this telecommunication part and what all the parameters you can use for designing your optical fiber and the most important factors for designing of a optical fiber. So now related to the users means those who can use this like Optifiber, the user can with the Optifiber, the user can design a multi-layer fiber with an arbitrary 2D reflection, or you can say the 2D refractive index profile, which is basically responsible for the reflection part, and each layer of a fiber will be responsible for that. Either it is a with a lower refractive index or with a higher refractive index. So you can use it for designing of a multi-layer fiber, and also you can use it for designing a profile either by defining the profile internally or using a library of built-in functions. It is not important that you specifically use a specific criteria to design a optical fiber, but you can also ask a manufacturer or a fabricator of a particular fiber to provide you the detailed specifications, that is the technical specifications, with which you can set all the parameters related to an optical fiber. So let us parallelly move to the software part. So here we have a Optifiber. Let me share entire screen. So this is optic fiber used to design a index profiling, or you can say composing the parameters of a actual fiber before you proceed for its manufacturing. So under softwares where you have installed it, you can get this folder Optifiber, and this is the logo. You just need to click this, and this toggle will open. So from here you can choose new, or you can open the samples. So let us use a patented file designed by Corning, SMF28, single mode fiber 28. So this will be like step by step. Once you install this, you will get the documentation as well. If you look into this section of Optifiber documentation, and under Optifiber documentation, you can see Optifiber manual and release notes. So this is the manual. So you can uh, go step by step how to get start with how to design a fiber profile. So there are multiple people wanted to join. Okay. So under this section of manual, so I will repeat it again, those who just have joined. When you have installed this Optifiber software, under this section, you can get Optifiber documentation. Similarly, in case of OptiSystem also, you can get OptiSystem documentation. So for each module, you can look into the manual and you can go through the guide so that you can design your own optical fiber. So I hope this will be helpful. Coming back to the software part. So these are the steps. So first of all, design a fiber. So region 1 and region 0 and region 1. Basically, these are core and cladding. So core is with like a position of 4.15 width, a very normal width, and this is the refractive index. So these are basically region 1 and 0 are the core and cladding. So you can define the parameters of core and cladding individually. You can name it here. You can set the wavelength 1.3 microns. Basically, this is approximately 1300 nm wavelength, and the profile we have chosen is constant. This is the refractive index. This is the width. And in case you want to define the properties of a material, means the choice of material related to core and cladding, individually you can define it from here. So right now it is pure silica, then 3.1% germania doped silica, and 1.0% fluorine doped silica. So again, you can define it using the Selmier coefficients. So these coefficients means the same formula and their coefficients are easily available through Google or research papers. So depending upon the material, like this is a pure silica, you can find the same coefficients from the research papers as well as from the Google. You can search it out. So similarly, we have other materials as well: fluorine, germania, pure silica, and so on. So basically, rest are the fused one, or you can say the doped one. And you can also add the doping part. Just a second. So I hope there are enough people, those who have joined. So we were at defining the material for core, and then the another region cladding. So the width is different. It is wider. A refractive index has been changed. And then click to apply, and then OK. So all these parameters, like these are the parameters related to the actual designing parameters of optical fiber, and these are the patented parameters of Corning, those who have designed single mode fiber 28, SMF 28. Now calculate modes. So you must have heard about the LP modes in finite difference or matrix method. For more detail, you can read from different materials available online related to finite difference method and matrix method. So you can define the LP modes, you can recalculate it. So these are the modes of a fiber profile, and you can export this, and you can also import this depending upon the requirement. This is the order from 0 to 10 order, means 10 time it will inject the laser. Then composition, and under composition you can again calculate it, and you can see the power as well as the field. So basically it all depends upon how you have defined the LP modes. So the mesh size is 100 by 100, that is X and Y. Then the next part is scanning the fundamental properties. So here you have the wavelength. Now these are the most important parts of a optical fiber. So you have the licensed version of Optifiber in your lab. So you can talk to Dr. Tripathi, your HOD, and you can get the license, and even we can provide you like 30 days license. So here you can calculate GDV, that is group delay or group dispersion velocity. Then mode width measures, material loss, bending loss, splice loss, effective nonlinear coefficient. And further under material loss, again you can define the absorption criteria, because in environment or as per the material conditions, you have to define its absorption properties that comes under the material loss, like OH absorption, IR absorption, UV, relay scattering.
Sir, I am unable to hear you.
Sorry. We'll explain it again. So under these LP modes, first of all, you have to define the finite difference and matrix method. So once you define this, either LP mode with finite difference or matrix method, you need to calculate it. After calculation, you can go for its composition. You can calculate and see the power and the field respectively. This is the field after laser is injected. So you can use these structures in case you are compiling a project for this optical fiber designing. So once you are done with this, go to the fundamental mode properties. Here you have group delay and dispersion, mode width measurement, material loss, bending loss, splice loss, effective nonlinear coefficient. So these are the most important part for defining the fundamental modes of an optical fiber. So first of all, if we want to define the material losses, basically these are the absorption parts. So these absorptions are related to the material properties, which kind of material you are using for making your optical fiber. Depending upon that, you can define the absorption values like amplitude, wavelength, and width. And this is the fit method. Fit method means this is the predefined method relative to the material and its properties. Every material has its own fit method. For example, if you search on Google or search any research portal regarding the fit method or the fitting numerical formulas for particular material, so you can get it using these values. Then bending loss. So again, this bending loss depends upon the formation of macro bending loss model 1 and model 2. So you can use it, you can calculate it, you can assume the bending radius in mm, you can mention it here and then calculate it. So it's better to define everything here and then at last you can calculate. Then the splice loss. Under splicing loss, again you have to mention the values like matching mode size, medium refractive index, transverse offset. See, all these parameters are like maybe very new for you, but in case you have interest, you can go through the tutorials available, and also you can search online related to these parameters. So basically this is a pure physics part. Then at last go for the calculation, and after calculation it will set up with your profile. Then cut off, again with the mode solver, recalculate, then calculate the cutoff. You can get the cutoff values. Then by references will help you to define the data related to photoelastic constant or perturbation this parameters. So perturbation will provide you basically the thermal coefficients. Like if you want to mention the thermal stress, you can mention the thermal coefficients here. Like it should work under the circumstances of minus 1000 degrees Celsius. So depending upon these parameters, you can give the intrinsic and strength formation of a optical fiber. So which is important because you only knows at which atmospheric conditions or environmental conditions your fiber will be in use. So accordingly, you have to mention all these parameters. Then PMD. So PMD we have mentioned. So at last, in case you want to get all the values in a table, you can get it in a table like radial distance with respect to refractive index. You can save the same data into a text file, and these are the calculated results. So these results are more than sufficient as a specifications to get your optical fiber manufactured, like modal index, group delay, waveguide dispersion, material dispersion, total dispersion, near field MFD, far field MFD, and so on. So you can print this, you can save this, and after saving this, you can hand over the file to a manufacturer who can make optical fiber for you. And below, we have the relative graphs. For example, this is the refractive index with respect to the radial distance. And this is the effective and group indices. In other words, modal index with respect to the wavelength, starting from 1.2 to 1.6. Group delay, dispersion, mode measurements, material loss. So here, as per the color coding, the legend is defined. This is the bending loss, splice loss, and this is confinement, mode field, and that's it. So in this way, you can design optical fiber. I can understand this is a very new concept for you, and merely you can understand the technicalities of this optical fiber designing. But at least in case you have interest, I recommend you to go through this Optifiber manual, and through this manual, definitely you can able to design your own optical fiber. And also, along with this, once your this Optifiber is installed, under documents and Optifiber samples, you can find the actual data of the fibers that is being manufactured. So this is related to designing of an optical fiber. So coming back to our slide. So here we were discussing about how you can use the inbuilt functions. You can import an external profile, and you can also check it or scan it through NR9200. So NR9200 is basically the model, or you can say the hardware, basically to scan your designed fibers. So this model is basically provided by Expo. So this is also a Canadian company, and they have their presence in India as well. So you can assign the material dispersion based on Selmier model. Model the material losses. We have already seen that. And you can characterize this using modal, fundamental, or higher order, which includes mode field pattern, group delay, effective refractive index, group velocity dispersion, mode field estimations, macro bending, and so on. So this is how you can extract that data using Optifiber. And regarding applications, so this is important for you to understand wherever you can utilize this structure. So it assesses parameters, sensitivities, and tolerances, fiber mode solving of LP or vector modes by finite difference or by transfer matrix method, analysis of measured fiber profiles from instruments such as the Expo, single mode fiber designs such as Corning SMF28, dispersion flattened or shifted fibers, multi-mode fiber design, visualization of multi-mode interference pattern, automatically parameter scanning, fiber sensor design, and calculation of bireferences and PMD from intrinsic or extrinsic perturbations. So see, I again recommend you, just in case you have interest, you can have this PPT, you can correlate it with the manual once you install Optifiber, and also go through the research papers, go through the companies, those who manufacture optical fibers, and try to get the data sheets. For example, if you have designed this Optifiber here, and now you want to see in Opti system, let us open this Opti system. So under Opti system, if you look into optical fibers library, we have fiber with length 50 kilometers, which we have used yesterday. So here you can define wavelength and everything, and dispersion, then PMD. So these are the same coefficients, or you can say the same parameters you are defining in Optifiber. So accordingly, you can define all these parameters once your optical fiber design is ready with Optifiber, so that you can also correlate it. And you can also use the same parameters here so that you can check how it is behaving. Okay, any question related to Optifiber? Because now I will be starting with the Opti system again.
No, sir.
Okay. So yesterday we have compiled a project. So this was the project for 10 kilometers. See, using this platform, specifically Opti system, you can create a lot of projects for your final year. Even let me explain you, a lot of government agencies and even the research institutes and even your institute as well, they apply for external funding related to research. So these type of softwares help you people to grab the projects and to fulfill the eligibility criteria, as well as you can like come to the conclusion with the aim of experiment or the project. You can complete that, you can conclude that. Now, yesterday we have designed a system with 10 kilometers of range, and this was the perfect thing. It's too late to join. So it was 34.88. What if I connect optical amplifier, because amplifier always enhances the signal. So we have here amplifiers library, optical, and we have various kind like EDFA, EDFA black box, optical amplifier with gain. So like apart from all these, you can use semiconductor optical amplifier, then Raman amplifier, and then doped fibers like erbium doped, ytterbium doped, and so on. So all set of fibers are available, but I will be using this optical amplifier. This is common, or you can say the generic one. So this optical amplifier, so in case you could get a chance to see the actual device optical amplifier, you can go through the data sheet. Like for example, here if you click on the help button, you can get its data sheet with all the parameters like operation mode, gain, power, and everything is mentioned here along with the technical background. So every device has its data sheet. So here it is under gain control with 20 dBm. So what if I choose power control? Power control is 10 dBm. And now if I simulate this, it is somewhat very similar. And again, here now it's a R&D part. Instead of 1 milliwatt, what if I use 10 milliwatt? 36.6. It is improved. The quality factor has been improved. So it means that there is a chance, like by increasing the power factor, you can optimize your design. 37.399. It is again improved. So in this way, because you have to look into the devices and their parameters, how you can improve that, either by increasing the power or using the amplification method like gain control. What if I use the gain control method? Will it help us? 37.67. It's almost similar. And what if I now change the length? Now, if I come to this report section under view project browser, so here I can get the graphs or analysis portion of all the results. So under PER analyzer, you can check out the amplitude histogram. Then you can check the probability. So these are basically the graphs with respect to the analysis, eye amplitude, eye closure, then eye diagram, and then Q factor. So these are the important segments here. Now, what if I want to plot some graphs in relation to the change in length of a fiber? So in that case, you have to choose optical fiber under kilometers. You have to change the mode, that is the sweep mode. You need to mention the iterations. For example, it is for 10 iterations. Linear. So I want to see from 10 kilometers to 100 kilometers. So my result will be recorded for each 10 kilometers. 10, 20, 30, 40. So at every these values, my values or analysis will be recorded, and accordingly, I can analyze the system parameters, or I can analyze the optical system I am designing here. Click on OK. Again, this one. Now let us simulate this. So it will run for each sweep iterations. Calculation is finished. Now, if you look into this, so this result is at 10th iteration. So we can change the iteration, means for first 10 kilometers, then next 20, 30, 40, 50. As soon as the length increases, your values or your results tends to degrade. 60 kilometers, 70, 80, 90, and 100. So at 100 kilometer, my Q factor is just 5.8 and I is crumbled here. Eye height is very less and there are like almost ISI, intersymbol interference. So this part is intersymbol interference. So which is not a good section for optical communication part. Also, you can create a report here. Click on an empty graph, Opti2D graph. Now, choose optical fiber, then parameters. Under parameters, you have given a sweep length, drag and drop it to either x-axis or y-axis, depending upon how you want to present your graph. So I am placing it at x-axis. So this is the length in kilometers from 10 to 90. And with respect to this length, now I can draw all the relative information, like first of all, maximum Q factor. So I am placing it at y-axis. So this is my maximum Q factor with respect to length. So now you can see as the length of the fiber increases, your Q factor decreases. At 70, it jumps out, but again it drops down. Similarly, another factor which is minimum bit error rate. So if I replace this maximum Q factor, so this is the minimum bit error rate. Until 90, it was good, but after 90, your bit error rate increases. You can see the coordinate values at export data, and these are the respective values of X and Y. So these are the lengths in kilometer, and these are the respective bit error rates. So you can see after 90, it reaches 2. And similarly, with respect to a receiver part, in case we want to see it with respect to the receiver part, you can choose pin photodiode, then results, and then average photo current with respect to length. So this is your average photo current with respect to length. And what else? And now with respect to length, if you want to check out for other parameters, like maximum signal to noise ratio, so this is how maximum signal to noise ratio is varying with respect to length. And similarly, if we talk about the minimum optical signal to noise ratio, so this is minimum optical signal to noise ratio. You can go through this properties, y-axis. You can change the color, or you can like change the definition value. So maximum SNR and minimum optical signal to noise ratio. So this is the legend. You can copy and paste it on a clipboard, means to your Word file, you can paste it. Any questions?
No, sir.
Okay, so these are some of the important factors. Similarly, if I remove this sweeping and put this for 10 kilometers of length only, and instead of changing the length, what if I change this power? Normal to sweep, 10 iterations, starting from 1, sorry, starting from 1, to, you can say, 25 dBm. So from 1 to 25 dBm, these are divided with 10 iterations. Now, if I go through the simulation, okay, now if you look into this BER analysis at 10th iteration, it is 37.95 means at 25 dBm, at 1 dB, 3, 4, and so on. Means just look into the iteration type. So as power increases, the Q factor increases here. So similarly, you can create a report here. And this report will be created using CW laser because we have given the sweep parameters to power. Power at the transmission side and the total signal power across fiber. So as the power increases, the total signal power increases across optical fiber. And in case as per the layout, I have connected this RF to pin photodiode. Mm, oscilloscope is there, okay. So as per this layout, electrical. Okay, so this is the electrical power. Yes. This power with respect to the power at a receiver section. So this also keeps on increasing. So this is vice versa process to check how your receiver is behaving with respect to changing or increasing the power at the transmission side. Also related to other results. So this is the maximum quality factor. So with the increase of power, so if you want to define a particular section where the maximum power is achieved with the maximum Q factor, you can go through this data and here you can check out at which power level you have the maximum Q factor. So 39 is at 19.66. So this is the actual value of power where you are getting the maximum Q factor. So this is the way how you can optimize your signal for a better quality factor. Along with that, you can also check out for minimum bit error rate. So this is the point. So from here, just look into this data. So you have the perfect bit error rate at 17 and 19.66, 0 and 0. And the rest of them, like they have the higher value of bit error rate, which is not good. So power level at 17 dBm and 19.6 dBm works for you. So these are the points you can mention. You can collect the data, and while making out your project, you can mention these points along with the graphs. So it will help you out. So this was all related to optical fiber communication. Let us save this, and also let us make a copy for the next one. So the next part will be related to optical wireless communication. So which is very interesting. Let me open this section. Let us go directly to this optical part. Yes, this one. So free space optics. Let me read it first of all. This FSO or free space optics in optic system refers to the simulation and analysis of optical communication system that utilize free space propagation of light, typically through the atmosphere, for transmitting the data. In optic system, FSO simulations involve modeling various components and effects relevant to FSO systems, including optical transmitters, receivers, atmospheric attenuation, turbulence, and pointing, tracking, and acquisition system. See this first point in relation to FSO and in relation to this PTA systems. Basically, these are, you can say, the most scientific progress taking care by our defense organizations. They are doing a lot of research on this, and they are like manufacturing and coming up with the new devices, new kind of inventions in the field of FSO utilizing opti system, and it is also helping a lot. So in drone systems, or you can say in UAV systems, the unmanned vehicles, you can say, so these systems are very efficient to maintain the communication from ground to that particular drone device or whatever the device flying in the air, either it is airplane or a fighter plane, jet plane, unmanned plane, or any other device, right? So this kind of a communication is very helpful for these projects. So let us come back to this section and delete this optical fiber. Now, under this free space optics library, you have FSO channel, then optical wireless channel, Li-Fi, FSO weather conditioning, and so on. So now we will be using this universal FSO channel. So instead of fiber, I'm connecting this one. So for FSO, let me tell you, you do not require any license from Telecommunication Department of India, because like in regard to other communication part, for example, fiber communication or GSM based communication or any uh, like satellite based communication, so you need a specific license. You have to buy the license. You have to get registered yourself for doing such kind of communications, because it is directly interfering the RF communication part of our Indian subcontinent. So that is the only reason the regulatory authority, that is Telecommunication of India, that is a government department. They provide you with the licensing and registration part. But in case of FSO, free space optics, you only require two telescopes. One telescope is at the transmitter side, and one telescope it as the receiver side. Right now, if you study more about the geo, so geo has have come up with this FSO features. Right now it is very limited, but installed in a lot of MNCs, where you can find like a 2 or 3 kilometers of a area, the maximum area, or even in the campus. For example, in your campus, if you have 4 to 5 buildings or 6 buildings, so at a shorter distance you can install these kind of systems and without any licensing, and it will be very efficient. But this also restricts along with the environmental conditions. For example, if it is a heavy fog environment, so there will be a disturbance. If it is a heavy rain, then again it will be a like a very disturbance will be created in the communication part. So if I double click on this, so from the parameters you can get to know how it is working. First of all, you can define the range. For example, here by default range is 1000 meters, that is 1 kilometer. Then you can define atmospheric attenuation. So you can define the atmospheric attenuation either of your own, or you can choose this FSO weather parameter. So if it is user defined, you can mention your attenuation part. So attenuation is the main factor. In case you want to read research papers related to FSO, so during that process, you can get to know regarding the attenuation factors. So basically, these are affecting a lot of main losses in regard to communication. Then we have some geometrical losses, free space path loss, geometrical gain, then transmitter setting. So these are the telescope settings basically. So these are inbuilt in this system. Beam divergence, transmitter aperture diameter. So basically we are talking about a lens inside a telescope who has some beam divergence. You can mention at which angle you want that. Then transmitter aperture diameter, transmitter height, then loss, then telescope gain, and so on. Similarly with the receiver setting as well. Now, if you define it using FSO weather parameters, so here you get a platform where you can define the atmospheric condition like dry weather, which includes clear, haze, and fog environment. So under the same, you can change it to the model type Kim and Cruise. So these are the models respectively with the research they have concluded, Kim and Cruise. Then for the precipitation, which includes rain and snow, again you can choose the precipitation type like rain, snow wet, snow dry, or your own defined precipitation type. Then clouds. So for example, if it is a hilly area, you can say above 2400 meters of height. So there must be a cloudy area. And if you want to set up your FSO system, so there must be the possibility of clouds. So if the clouds are there, you need to choose the cloud type: stratus, cumulus, nimbostratus, and so on. So these are the types of clouds you can choose. So for example, if I choose dry weather here, and if I click OK, let us see for 1000 meters if I can get some result. And for the iteration, let it be one iteration only. Change this power to 5 dBm only. And now let us simulate this and see if we can get some connectivity. It is simulating. So it gets simulated. I can see 73.7 Q factor with zero minimum bit error rate, which is very good. And it is a excellent projection. And in this way, we have successfully compiled this 1000 meters range FSO communication at an environment related to dry weather. Now, what if I change this weather condition to precipitation, means rain or snow? So earlier it was 73. Just a second. Sorry, we lost it. Okay, we lost the data. So for dry weather, for single iteration with 5 dBm of power, let us save this. So it is approximately 76 with zero minimum bit error rate. Now, what if I use this for precipitation, means rain and snow, and precipitation type, for example, if it is a rain, and rain, the precipitation rate you can set up 1 mm per hour or any like precipitation rate you can mention here depending upon the region. For example, for Cherrapunji, it will be different. It will be on a higher side. So depending upon location to location, your precipitation rate will differ. So if I simulate it, 68.16. Now it has been decreased because rain and rain particles plays a very important role to degrade your system, your communication system. Now, if I increase the precipitation rate here, or if I keep on increasing, for example, from normal to sweep, if I sweep it for 10 iterations and give the value from 1 to 10 mm per hour, it may take a minute. So this will help us to understand the phenomena of increase in precipitation rate with respect to the communication we want to establish using FSO. Any question till now? Anybody you want to discuss anything? Anyone? Say in case anybody from you want to work on a project or want to do some industrial training or something like that, we can provide you projects. We can compile it. You can parallelly uh, get it checked from your guide here in your institute, and this will definitely uh, create your better profile. This will help you in a long run. So about to finish. So simulation is completed. So if I check for BER, so this is at the 10th iteration, means if the rain is at the precipitation rate of 10 mm per hour, starting from 1, that is 69.45. Then if you keep on increasing the rate mm per hour, your quality factor keeps on decreasing. So in the same respective way, you can create the project report, universal FSO, parameters, and this is the precipitation rate with respect to, let us draw this again, precipitation rate with respect to the quality factor. So this is the quality factor. This is the minimum bit error rate, which is constant. And at last, if I look into the power we have left with, so this is the power. So at 10 mm per hour, your power will decrease a lot. So I do hope you understand this phenomena. And similarly, what if we use it for clouds? Let it be one iteration only. Calculation is finished. 0. The quality factor is 0. Maybe there is a chance if we increase this, or let me see. the stratus. Calculation is finished. So again 0 because the range is too high, approx 1 kilometer. Let us decrease the range, keep it to, or you can sweep the range. Let us go for 5 iterations only and just linearly 50 to 250 meters. Let us see if we get something. In the meantime, in case anybody has like any question, any doubt, you can ask me. So these kind of simulations requires a higher RAM. Right now my system is having 16 GB of RAM. So it is recommended at least 32 GB of RAM, for example, if you want to go through such kind of simulations. So that helps you with the faster simulation. It saves the time. So calculation is finished. So at first iterations, at 50 meters of range, you have 220 Q factor and minimum bit error rate 0. At 100 meters, it is 24. At 150, it is this. Means approx 100, or for better understanding, we can check out the range with respect to maximum Q factor. To be rest assured, so these are the values. At 100 meters of range, your Q factor is 24. Rest, you have 0. Similarly, for minimum bit error rate, so up to 100 meters, it is fine. Then it goes up, which is not good. And what if I want to see the total power left with? So your total power keeps on decreasing. So this is how you can play along with these orientations in relation to the various atmospheric conditions. And like there are a lot of projects you can create using weather, precipitation, or clouds, and even you can find some research papers using OptiSystem for FSO on IEEE, Scopus, Optica, and there are European journals, Japanese journals, and so on. Okay, along with this, so this all was related to free space optics, and telescopic based communication system without any actual wire, or you can say actual fiber. So this is in relation to the optical wireless communication. So what if I want to utilize the same concept for other applications? Other application means for underwater kind of a scenario, you just need to change this component with this non-line of sight underwater channel. Now, underwater communication has a lot of complexities because it depends upon the density of water, like for clear ocean, for pure sea, for coastal ocean, harbor, every type of ocean has their own attenuation coefficient. So accordingly, you can choose it, you can choose the frequency, and you can like choose the range. For example, right now the transmitter depth is 20, receiver depth is 20, horizontal distance is 25. So this is merely a very, very low distance. And in case you want to study more or want to do some more research, you need to simulate this and you need to get it 0, because we need to work on the wavelength nearby 532 nm, like visible light communication starting from 350 to approx 750 nm. And here the frequency of laser is 1550, let it be like 532. And here reference wavelength 532 again, that is approximate value. And we may not get the same at higher bit rate, so let us change it to some mbps, 10 exponential to 6. And let us see if we have anything here. Again 0. And what if I increase the power, for example 30 dBm or even more than that? It all depends upon, okay, I have like started getting some signal, maximum Q factor 3.7. Now I can understand I need to vary the power, let it be in watt. Let us use 10 watt of power. Now you are getting 23.7 of a Q factor along with BER 1.1. So this is fastest and as far as the result we can get at underwater communication in clear ocean. So accordingly, you can change the temperature, you can change the salinity, because it all depends upon the texture or density of water, water particles, and their index of refraction, their absorption coefficient, scattering coefficient, the transmitter, receiver, and horizontal distance or depth, and so on. So accordingly, you need to change the settings, and definitely you can get some results. There are a lot of papers published in relation to this underwater communication. Again, Indian Navy, defense, space research organizations in India, they are working a lot utilizing these kind of applications. Any question till now? Anybody? So from my side, the overview related to OptiSystem and Optifiber is over. So I'm like, I shall be waiting for the queries from your end in case you have any. And if in case you want to do some projects with me, So you are most welcome, and I can provide you my contact details, or you can write down to us at this email ID. So you can note it down, and in case you want to do some projects, please get back to me or our company and talk to your HOD first of all, so that he can guide you on which application as per your interest we can work. Any question, or should I wrap it up? Okay, thank you all for